So today I am going to talk about mathematics and physics, and they really in many ways are tightly interwoven and inseparable. And in fact, much of mathematics was developed to solve physics problems, and then sometimes the mathematicians get way out in front with abstract ideas, and the physicists catch back up with them and find that, oh, those ideas too are relevant to nature and deeply profound. And one of the most profound examples of that I know of is the spin of the electron. The mathematicians took the concepts of vectors, which many of you have studied in school, and they started thinking about what would be the square root of a vector. You know, after all, we think about the square roots of numbers like 4, and we find that the square root of 4 is 2, but it could also be minus 2. And then we start thinking about the square roots of things like minus 2. We find that that's the square root of plus 2 times the square root of minus 1, so we have to figure out what the square root of minus 1 is, and we invent complex numbers. So it seems quite natural that you might end up with something interesting if you take the square root of a vector. And so it turns out in the late 19th century, early 20th century, people thought about the square roots of vectors, and they invented things called spinors, which are funny little complex numbers. In fact, the thing that's so weird about a spinor, if you rotate a vector through 180 degrees, 360 degrees, it comes back to its original position. But if you rotate a spinor through 360 degrees, it's actually minus its original position, and you got to go another 360 degrees to bring it back. So you think that can't possibly have anything to do with nature, the square roots of vectors. Then along comes quantum mechanics and the electron. And the most basic fundamental particle that governs all of things in the world, chemistry, electronics, everything is electromagnetic that we actually can touch and access in our everyday lives. The electron is a spinor. It is not a vector. Its spin is the square root of a vector. How weird can that be? And if you rotate an electron through 360 degrees, it comes back to minus itself. You got to go through another 360 degrees to bring an electron back to its original position. And that's why you can't put two electrons in the same quantum orbital at the same time. Because if you could, and you say put them together like this on top of one another, and you rotated that system through 360 degrees, let's put it this way, if I exchange the positions of two electrons, that's like rotating one through 180 and the other through 180 degrees, and that'll give you minus itself. But that's the same system. So let me say it again. Two electrons sitting on top of each other, the same spin, if I exchange their positions, it's like rotating this guy through 180 degrees and this guy through 180 degrees. But that's like rotating one spinor through 360 degrees, and it changes sign. So something can't equal minus itself. It has to be 0. So you can't put two electrons in the same orbital at the same time. You have to put one in, spin up, the other spin down. Then you get helium, and then you have to go to lithium. How weird can that be? So that's an example. So did that probably too fast for you, but that's an example of a profound insight into nature that was borrowed from the mathematicians who got ahead of the theoretical physicists. But the mathematicians got there in the first place by thinking about physics and vectors and fields and things that physicists have been playing with. And that's the dance we do between physics and mathematics. And nowadays, things like string theory drive ideas in knot theory, and those ideas come back to define how string theory might work. And someday, maybe all of that's going to be useful. I think it will be. Mathematics generally always becomes profoundly useful. And it's also very cheap. It's a very inexpensive field of research. And eventually has very profound insights. So I want to talk about another example of this. And perhaps one of the most profound examples. And it's fairly easy to get an appreciation of. And it's symmetry. It's the relationship of the basic concept of symmetry to nature. In fact, what we are trying to do in physics is organize our thinking about nature. Science proceeds by sort of making a bunch of observations, then trying to say this thing's bigger than that thing, this thing's stronger than that thing, put them in some kind of order relationships, eventually try to assign numbers to this. That thing's 10 times bigger than that thing. That thing is 1/3 the strength of that thing. We need units, centimeters, grams, seconds, and so forth to start doing that. Then the ultimate thing is to have some organizing principle. Some principle that says, well, there's a reason why that thing is 10 times the mass of that thing, because it's got 10 of those in it. And you begin to see that atoms, for example, increase in mass because they have more neutrons and protons inside of them. That's a profound thing, that the atomic structure was not understood until the 20th century. And with that comes enormous capability then to put it to work. That's not really our goal in science. We're trying to understand it. But it's always been the case that when we understand it, we can put it to work. So it always proceeds in those four layers. Back in the 1960s, when all these elementary particles were being produced and nobody had a clue what is a rho meson, what's an omega, what is a phi meson, what is a delta resonance of the proton. All these things were being seen at accelerator laboratories. The field was very much in a classification era. What are these objects? First of all, let's make a list. And what's the relationship between those objects and those objects? And eventually we could put them into groups and say these objects will always be heavier than those objects because they're in the same sort of collection. And then eventually the big breakthrough came around 63 through 72. We realized the reason for this complexity is that those particles that were being made had tiny things inside of them called quarks. And that the quarks were actually photographed, if you like, for the first time in about 1970 at the Stanford Linear Accelerator. And that was the beginning of a deeper level of understanding. What are quarks? What governs their rules? And now we're back to a pattern. We've got 6 quarks, up, down, charm, strange, top and bottom. Top is very, very heavy. Up is very, very light. We don't have a clue. Why? We don't even know how to organize them at this point. We know they sort of come in pairs and 3 sets of pairs and so forth. But what are the rules that are governing this? And we're searching for organizing principles. And it's not that we're completely random in our approach. We build on success, and we have discovered that there's something called symmetry principles that govern organizing principles. So that we use symmetry to try to figure out, well, if I put all the quarks together in one thing and I can rotate the top of my head into a charm, and then I have some sort of symmetry relationship between them, then to understand the mass difference, I have to understand what could generate a breaking of that symmetry. That's how we think about it. Symmetry has become fundamental to our understanding of the basic laws of physics, and that's not going to change. It's going to stay that way forever. We've really uncovered one of nature's basic leitmotifs, as they say in opera. There's a basic theorem that I want to tell you about today. It's a mathematical theorem that connects symmetry directly to the laws of physics. It takes this mathematical concept and just connects it directly to the laws of physics. And the deeper we go, the more it just defines the laws of physics for us. And it's called Noether's theorem. And it was discovered in the 20th century. And I think it is as important to us as the Pythagorean theorem. The 2 most important theorems in nature are the Pythagorean theorem, which defines sort of what we call metric geometry, the concept of distance. In any, whether space is curved or flat or whatever, you basically start with something like the Pythagorean theorem. And Noether's theorem that basically brings the symmetry principles into the laws of nature. So Noether was one of the greatest mathematicians who ever lived. She's a woman, born in the 19th century, didn't live very long. She is the first person to break through the glass ceiling in the German academic system. The German academic system from the mid-1800s to about 1930 was the preeminent place in the world. It was the place you went if you really wanted to make it in almost all disciplines. Mathematics, physics, chemistry, music, even art, architecture, and so forth. You wanted to go to one of the German universities. And it was an incredibly liberal environment where anybody who was good at what they did would make it in that environment. But they had this problem of gender bias that prohibited women from becoming essentially professors. And Emmy Noether was the first person to break through. She had a little help from some friends who recognized how profound her theorem was and how profound her work was. And they wrote letters continually to the rest of the staff at the University of Göttingen, Germany, where she was. That's where Hilbert, who was considered the greatest mathematician of the era, lived. That's where Heisenberg is from. He was there then. So quantum mechanics and topology, Felix Klein was there. The topologists were all there. Had this great mathematics, physics department, and that's where she was finally promoted. I think in about 1931, and the next year some awful things started happening in Germany, and they fired basically everybody who was a minority, woman, whatever on the faculty, and she had to leave Germany. She was lucky to be able to come to Bryn Mawr University, where she lectured until her untimely death in 35. So what is symmetry? Well, you sort of know it when you see it. Here's an example of it. I actually took this picture, I think in 1981, and it ended up in our book. And that's why you should always keep pictures that you take. If you ever want to write a book, you're much better off putting your own pictures in the book, because it takes forever to get permission to put somebody else's picture in the book. And it's really hard to get permission to put a picture of Albert Einstein in a book, so we didn't even bother. But this is the famous Taj Mahal. And as you can see, the architects have built into this many different symmetries. It's a remarkable building. It's actually a tomb. It was built by a Muslim king in northern India for his deceased wife. And it is a remarkable structure in many ways. But the main point I want to make is it has a symmetry whereby I can identify an axis that sort of slices through the middle of the building. And I can imagine a mathematical mapping of every point to the left of this axis into every point, into another equivalent point on the right, and vice versa. So if you had a lot of construction workers and they could go and remove a little piece of marble here and haul it over here and put it in there, and vice versa, put that piece there and so forth, and do that quickly, you'd end up with the same Taj Mahal. So what you see here is there's something we call an operation that you can perform, either get your construction workers to do this physically or actually imagine it mathematically or abstractly, that maps points from left to right and right to left, and preserves what we call the invariance, the unchanging quality. It preserves the form of the Taj Mahal, which you started with, you get back again. Notice that in this picture there are things like clouds that were a little bit lopsided that day, and they break the symmetry, so that cloud ends up looking like that cloud, but the Taj Mahal has the symmetry, and that's what we're focused on. So symmetries involve, well, if we ask for a definition, I've taken this poll, I could probably take it with you to define it. The sorts of things I get are answers like things that look the same when you see them from different points of view. It's like the sides or angles of an equilateral triangle, they're all the same. Different parts of an object look the same, like eyes and ears of a face. But a more scientific or precise way of saying it is there's an invariance or an unchanging quality of a system or object under a transformation or a collection of transformations. So what we just looked at was one transformation. The object was the Taj Mahal. It didn't change when we did the transformation of reflection about the axis. And notice that what really underlies all of this is the most fundamental thing in mathematics, an equal sign. Taj Mahal before symmetry operation equals Taj Mahal after symmetry operation. So this is a form of things you can do that preserve that preserve what we call an equivalence class. Makes before and after are equivalent to each other under the symmetry. And in physics, we basically have two types of symmetries, and they're really fundamentally different in a basic way. Discrete symmetries and continuous symmetries. So for a discrete symmetry, you can consider a chess piece on an infinite chessboard, and you can forget the colors of the squares. So I have a rook which doesn't care about the colors of the squares. And if I put the rook here and he looks around at his universe, it looks a particular way to him. If he takes 3 steps to the right and 2 steps up, he ends up over here. And if he sits there and looks around, the universe looks the same. And the reason is that there's an enormous symmetry of this system. It's the sets of discrete hops I can do from one square to another. I can go any number of hops in the x direction, any number of hops in the y direction. That's a transformation of the chessboard. Chessboard looks the same since it's infinite, and the rook looks around and doesn't feel like he's moved at all. There's nobody else around to talk to, so it looks exactly the same. Why would this be useful in physics? Can you imagine anything that this is a symmetry of that we would deal with in the laboratory? Well, how about an electron in a crystal? Or an atom in a crystal? So if you put an atom in a crystal of sodium chloride or something, that will have a discrete symmetry, and the behavior of the atom here will be exactly the same as the behavior here. If it's a chaotic mess, like a liquid, or if it's some complicated molecule and the atom moves around, it's seeing a slightly different environment when it moves, and so the atom will react differently. But in the case of the infinite crystal, perfect crystal, there's a symmetry. And that symmetry really simplifies the problem of understanding how electrons and atoms behave in crystals. And on the other hand, we have continuous symmetries. And does anybody have an idea? So here's a continuous symmetry. Imagine a wine bottle with the label removed. And I have a z-axis. And I can rotate, well, it's like my coffee cup here. If I don't have any of the decorations on the cup, I have a z-axis, and I can just rotate the cup to a different position, and physically the cup is no different. The atoms and molecules were not affected by that rotation. In fact, if the coffee rotates, it's still the same coffee. It hasn't undergone a change. So there's a symmetry of this system, rotations about the z-axis. And these are continuous. Does anybody have a clue why this is a different, conceptually different symmetry than this? It's hidden in the word continuous as opposed to discrete. What's the difference between a continuous symmetry and a discrete symmetry? And is anybody taking calculus? Because this is fundamental to calculus, you are. Well, the difference is that there's no smallest rotation you can do, no smallest transformation you can do on the coffee cup. You can rotate it through pi over 2, 90 degrees, but you can also rotate it through 10 to the minus 50 radians, if you wish. And that's also a symmetry transformation. Whereas for our rook on the chessboard, there's one discrete minimum step. One step the rook has to take to be back in a new cell that looks equivalent to the other. And there's no 0.0001 step. And that means that actually, for those of you who are taking calculus, you can apply calculus to this, because calculus is designed to understand the properties of continuous mathematical functions. And once you have a continuous mathematical function, you can zoom in at arbitrarily short distances and ask simpler questions about the function. So here's let me write an example. Very apparently complicated looking function, but it's continuous. And that means I can go into any point on the function, let's say here, and zoom in. And if I zoom in enough, I basically see something that just looks a lot like a straight line. And if it's still wiggly, zoom some more, because it's continuous. You can do that infinitely. So once it gets to be, this point P, gets to flatten out, I can now talk about something very simple. It's a property of a line, which is the slope of the function at that point. And we call that slope, if this function is y equals f of x, we call this the rate of change of the function with respect to x at that point. If I know the rate of change of the function at that point, I can reconstruct the function. And maybe the rules for this function are simpler when they're looked at that way. And in fact, that's how physics works. If you have a particle at point x, its velocity is the rate of change of the position with respect to time. Now that velocity could be changing rapidly, being very large, slowing down, so like when you're on an airplane ride or it's bumpy or something, it's a rapidly changing function of time. But if you break it down, the velocity is rather smooth. And in fact, the laws of physics that govern the motion involve the rate of change of the velocity with respect to time, something called the acceleration. And Newton realized that the mass times the acceleration equals the force. That's the law that governs motion. It's not the third rate of change of position. It's not the 27th rate of change of position. It's the second rate of change of position, the acceleration. And we sometimes write that as a second derivative. And this, so what Newton did is he realized you could break up into tiny, tiny intervals a very complicated motion. And what's happening in a very small unit of time, a small increment of time, is always a universal equation. And then the problem is to, if you know the force, work backward and find the motion. And of course, you all know that the most incredible thing Newton did was to realize gravity had a well-defined force law. The force of gravity is a constant we call Newton's constant. So the force on mass 1 due to mass 2 is this. It's actually a vector. It's the unit vector pointing from one mass to the other. And that must equal, let's say, if that's the particle that's moving, that's the sun, that equals m1 times the second derivative position with respect to time. And Newton solved that equation. He was able to work backward and solve it. And he found Kepler's laws, dropped right out. Elliptical planetary motion, the conservation of angular momentum, all those things. So that's what continuity allows you to do. But it doesn't work with discrete function, with discrete things. If things are really, you can't apply your microscope and blow it up to look like that. You can't use calculus. Here's a function that doesn't allow you to use calculus, one that just has steps in it. Okay? Because if I go here and I blow it up, you depart here and you arrive there in an arbitrarily small step. I can't talk about the slope. All I can talk about is the step. And it's very hard to analyze discrete systems in abstract way. It's of course, when you use computers, you end up making everything into some discrete thing, but you're still solving the underlying continuous calculus equations of motion. But to analyze discrete symmetries is very hard because of the lack of continuity. But here, people were able to figure out all possible continuous symmetries that can possibly exist. So let me show you how that works. How do we think about symmetry? And I'm going to start with a discrete symmetry as an example. It's a fairly simple example, but it's sufficiently complicated that I think in about 3 minutes, if I don't talk too much, you're going to be really astonished. So what I have here is an equilateral triangle. You all know an equilateral triangle. It's the standard 120 degree, 120 degree, 120 degree equal angle triangle. DDD equal sided triangle. The inner angles all add up to 360. Did I say that? That's wrong. This is 60 degrees. I'm being stupid. 60, right? Yeah, so this is incorrect. In fact, 2/3 of pi is 120, so this would be 2/6, 1/3 of pi. Inner angles add up to 180. Sorry, factor T error in this. I want to do an experiment. Fortunately, symmetry doesn't care about the angles. It cares that you can do rotations and things. It doesn't care about the value of the angle. We'll come to that in a moment. So I'm going to start with a triangle that I'll call this a reference triangle, and I'll imagine I've glued it down on maybe a table or something. And I've given it what I call axes, 1, 2. By the way, I threw that in to see if you were awake. I obviously wasn't when I made that transparency. So here's my reference triangle, and axes 1, 2, and 3. And here's a action triangle. And I'm going to overlay the action triangle on top of the reference triangle. So the A's, B's, C's, Roman numeral 1s, 2s, and 3s, those are just things that we humans put in so we can sort of see what we're doing. It's very important to realize that. Coordinate systems, labels, those are things coming from the human brain that are added to a system to try to figure out what's going on. We're really interested in the heart of the matter, the stuff that doesn't depend so much on those labels and axes. So here's the question. If I have one equilateral triangle overlaying another equilateral triangle, how many ways can I pick up the overlay triangle, the action triangle, and put it back down on top of the reference triangle? How many distinct ways can I do that? Okay? And you have to be careful with that because we don't care so much about, you know, the path that we took when we pick it up and put it back down, whether I go 10 feet or just a few inches in doing it. And I don't care if I, in fact, run out that door and come back in that one with a new position. I just care about how many equivalent mappings are there from one overlay position to another. All right? Does anybody already have an idea? Well, let's do it. We can do an experiment. Well, first of all, we could rotate through 120 degrees. This is a real 120 degree rotation. I'm going to rotate about the center through 1/3 of 360 degrees, through 1/3 of 2 pi. That'll bring the vertex A down here, vertex B ends up over here, the vertex C ends up over there. That's a symmetry operation. So I don't care how you do it. You could pick the triangle up, run around those posts 30 times, come back and put it back down. The point is there's one and only one mapping of the triangle from the initial position to the new position, which we call this rotation through 120 degrees. Let's hit the reset button. Go back to where we started. What else could we do? We could reflect it like we did with the Taj Mahal about axis 1. So what have I done now? I've said there's an axis here, and I'm going to take every point to the left of the axis and map it into an equivalent point on the right, and vice versa. Well, that keeps A where it was, but it switches B and C. And so I'm going to end up with B was here, remember we go around clockwise, A, B, C. Now C is here, and B is here, and vice versa. What else can I do? Hit the reset button. Got 2 of them. How many more are there? What else can I do? Reflect about axis 2. Boy, you read my mind. If I take axis 2, I now reflect about that axis. It means I map every point on this side of the axis and into an equivalent point on that, and vice versa. And you see B and A are now interchanged, but C is the same. Reset. Well, obviously now I can do a reflection about axis 3, and that will interchange A and C, but it'll hold B fixed. Or we can rotate through 240 degrees, and that will rotate A all the way around to here, B rotated to here, C ended up here. Anything else? Is there anything else? Well, what if I did a rotation through 480 degrees? Hit the reset button and rotate this thing through first 360 and then 120. What do I get? Well, A will go all the way around and then it'll end up here. And B will go all the way around and end up here, and C will end up here. Is that a new symmetry operation? You're shaking your head in the right direction. Why is that not a new symmetry operation?
Because you've actually done it before when you only rotated 120 degrees.
Exactly. It's the same operation as the rotation through 120. So if we were to count it, it's more like what path did you take? Today I don't care about the paths. There's a branch of mathematics that cares a lot about the paths, called homotopy, and homology is another related field, where you care about whether paths can wrap around posts 10 times or 8 times or 9 times or whatever, and whether they can be shrunk to a trivial point or not. We don't care about that today. as a homework problem to see what's involved, you might think about paths that live on the surface of a sphere. So here's a sphere, and a path starts here and it goes out and comes back. And that path can be shrunk back to a point, always. You think of this path as kind of like a rubber band with perfectly shrinkable material. You can just shrink wrap that thing down to a point. Question, are all paths on a sphere shrinkable to a point? No, yeah, they are. Remember where I put the starting point, you can go around the equator, I can just come up over the North Pole and shrink it. But here's a problem. Here's a donut. Are all paths shrinkable to a point on a donut? So now you see you have paths that are trivial, that guy, that can shrink to a point. But you also have a path that goes like that loops once around the donut through the hole. And that path cannot be shrunk to a point. And in fact, if I have a path that goes n times and then back, n times looping around through the hole, that cannot be shrunk to a path that loops m times if n does not equal m. So all paths on a donut can be labeled by an integer n that runs from minus infinity to plus infinity. Counts the different ways in which you can wrap. Is that the whole story? No. Because there are paths on a donut that can wrap around like that, like the white wall on a tire. And I can go 10 times around the white wall, or minus 5 times. So all paths on a donut are labeled by two integers, the through the hole integer and the white wall integer. So if you take the Cartesian product of the set of all integers with itself, you have what are called the winding numbers, or the topological indices of a donut. Whereas for a sphere, it's just the null set. That's the difference between a sphere and a donut. So work this out for a double donut. Did it wrong. Count how many different classes of paths there are in a double donut. There's a homopod. Okay? That's called homotopy. It's a very fascinating subject because it's a way of saying something about the global shape of something. It's the opposite of calculus, where you try to zoom in on the short distance part and say what's happening differentially in short distances. This is a statement about what's happening at very large distances, and maybe our universe is a double donut and not a sphere. That's a physics question. But that has nothing to do with this. And that's why we don't care about a rotation through 480 degrees compared to 120 degrees. And that's more a question about the path. So like I said, I could pick the reference triangle up, the action triangle up, and run around the post there 10 times and come back and put it down. That would have a winding number of 10 units around the post, homotopically, but it doesn't say anything about the equilateral triangle. It's more a statement about the universe that I'm moving. So here we are. We have the symmetry operations of the equilateral triangle, but are we missing one? Is there one perhaps that we didn't think of that's just under our noses? Pardon?
The zero.
Do nothing. What if we do nothing? We sort of already did do nothing when we did 360. In other words, a rotation through 360 is the same as doing nothing. And we ought to count that because it helped us to figure out that 480 and 120 are the same thing. So let's do that. And so now you see we've counted all of the inequivalent transformations we can do to map an equilateral triangle into itself. And you ought to know by now that this is the end. Because how many vertices do we have? We have 3. And how many possible permutations are there of 3 objects? 3 factorial. That's 6. There can't be any more arrangements of the vertices. So the number of symmetry operations equals the number of permutations. It can't exceed that. How many symmetry operations will there be for a square? No. 4 factorial is 24, but the number of symmetry operations is actually fewer. Can I borrow a piece of paper? See, I told you the equilateral triangle was the simplest case. And it's simple in the sense that the number of symmetry operations equals the number of permutations. Now I make a square, and I'll label A, B, C, D, and now I can rotate through 90 degrees and end up with D, A, B, C. That's a symmetry operation of the square. But if the symmetry operations of the squares equal the number of permutations, there should be a symmetry operation that gets me from A, B, C, D to B, A, C, D. It would interchange the upper 2 vertices, but not the lower 2. And to do that, I got to do this, which is not a symmetry operation. And I'll let you do the homework problem of figuring out the number of symmetry operations of the square. And what you'll find is 8. And the reason is that you can't count relative flip-flops of these guys to these guys, or these guys to these guys. You're dividing by 3. 24 divided by 3 is 8. Okay. Well, that's an easy problem. So go work it out for the cube. Count the number of symmetry operations for the cube. And when you're done with that, do the 4-dimensional hypercube. So here's a square. Here's a cube. You can draw that. You should be able to look at it and count the number of symmetry operations. But now I want you to do the 4-dimensional hypercube. So here's the 4-dimensional hypercube. You need a 4th dimension. So you just draw one. I'm on a 2-dimensional blackboard, so I can always draw a 4th dimension if I can draw a 3rd dimension. So there's the 4-dimensional hypercube. How many symmetry operations does it have? You begin to see what mathematicians are trying to do. They want to know the answer to questions like that. They want to understand nature. Now I've lost my little pointer. What did I do with it? Little controller. Where did I put it? Oh, here it is. Okay, good. See it right here. All right. So far, you're not astonished by this. This is just a kind of tedious little exercise, but we learned something from it. And we looked at this issue of equivalence. Rotation through minus 120 you might have worried about. That's equivalent to 240. 480 is equivalent to 120. In fact, any rotation about x is equivalent to x plus 360. All seems pretty straightforward. How do we know we got them all? And this was a deep question that got solved in the 19th century by a really remarkable character named Galois, Évariste Galois. And to imagine what Galois was like, think of the famous movie Amadeus with Tom Hulce playing Mozart, this brash, arrogant character who insulted kings and so forth. And that was Évariste Galois. But Évariste Galois was 100 times worse than Mozart. And in fact got himself in serious trouble with the French crown in around 1816 or so. And he ended up, the apocryphal story is that the authorities in France wanted to get rid of him. So they arranged a situation in which he had a romantic entanglement with a woman who was married. She happened to be married to the best marksman in France. The marksman found out about this, was deeply offended, and challenged Galois to a duel. And Galois really had no choice. And the night before, he stayed up. Rather than practicing shooting a gun, he wrote down all of his ideas on symmetry. And he arrived the next morning in the field of honor and was taken out immediately by one shot. Actually, it was a horrible death. It took a few days. People have argued that story I just told is a little romantic and really probably not the case. And it's probably more sordid and ugly than what I told you. But this guy was a genius, and he answered the question, how do you know you have them all? By inventing an entirely new branch of mathematics. And what he considered was combining operations. Very simple idea. What if I've done a rotation through 240, and I don't hit the reset button? Keep the triangle where it is. And now I do a reflection about axis 1. What do I get? So we do our ABC rotation through 240. A goes all the way over to here, so forth. Now remember where axis 1 was. It cuts through B at this point. So now I do a reflection about 1. B stays put, but C and A are interchanged. So ABC ends up as BAC after doing a rotation through 240, followed by a reflection about 1, without hitting the reset button. And if we went to our table, and we look it up, we'll see that for a reflection about axis 2, we'll get BAC. And that's what we got. We got BAC. Therefore, we've solved the equation. Rotation through 240 times reflection about 1 gives me a reflection about 2. So now it's not hard for the simple equilateral triangle to work out the multiplication table. So here it is. It's like one of those highway mileage maps. But there's a really big difference between this and a highway mileage map. So what do we got here? We've got the first operation we do, called A, say a rotation through 120. We follow it by another one, let's say a reflection about 2, and we get a reflection about 1. Trust me, you can go home and check me. That's what you get. A times B equals C. So if you want to go from Chicago to St. Louis, you look up in the map the distance, and you get, what, 300 miles or something, like a highway mileage map. But this is totally different than a highway mileage map. What's the distance from St. Louis to Chicago? It's the same as the distance from Chicago to St. Louis, I think. Is that right? Yeah, that's right. Well, we just did a rotation through 120 followed by a reflection about 2, and we got a reflection about 1. That's St. Louis, Chicago to St. Louis gives that. Let's do them in the opposite order. St. Louis to Chicago gives a reflection about 3. A times B does not equal B times A. Okay. Isn't that ridiculous? Here we did it. Rotation through 240 times reflection about 2 equals reflection about 3. If I do them in the opposite order, reflection about 2 times 240 gives me the opposite, gives me a different answer. The commutative law of multiplication does not generally work for symmetries. And you might think that if that's the case, this couldn't possibly have anything to do with nature. But can I borrow your book? Just we'll give it right back. All crumpled. All right, here's a book. There's the x-axis, there's the y-axis, there's the z-axis. I'm going to rotate about the z-axis. Now I'm going to rotate about the y-axis. Book ends up like that. Hit the reset button. Now I'm going to rotate about the y-axis, 90 degrees. And now I'm going to rotate about the z-axis, 90 degrees. Ends up like that. So what do we get? First time around I did z, y, got this. Yeah, the binding's back here. Second time, I first do y, followed by z. Ends up like that. This versus that. A times B doesn't equal B times A in nature. I'm sure you learned at some point the commutative law of multiplication in school. 3 times 4 equals 4 times 3. Didn't somebody tell you that law at one time? It also applies to addition. 3 plus 4 equals 4 plus 3. To me, that's a content-free statement until you give me an example of something in which it doesn't hold. And here's an example. Symmetries, this is an astonishing result we have here because this is also a magic square. Notice that every element of the this is called a group. Every element of the group appears once and only once in every column, and it appears once and only once in every row. That fact is what mathematicians exploit to be able to construct groups in general and to prove theorems about them, because it's a powerful constraint. Not just any old multiplication table can be a symmetry. It has to have certain well-defined properties. And I just showed you the book rotation doesn't commute, so it's got something to do with nature. Okay, so are you astonished by this? There's one other fact about this I should tell you. Group multiplication is associative. But it shows you how subtle the concept of associativity is. Let's think about that for a moment. Well, you know from school that 3 times 4 times 5 equals, what, 60? That doesn't matter as to how you do the multiplication. You can multiply 3 times 4, which is 12, then 5, which is 60. Or you can do 4 times 5, which is 20, times 3, which is 60. Doesn't matter how you do it. So in other words, A times B times C equals A times B times C. But if you think about what you're really doing here, it's quite complicated. What you're doing in this case is you're starting with A, following it by B, and getting a result in the bracket. Then you're following it by C. That's pretty simple. But over here, you're starting with B, following it by C, writing the result down on a piece of paper, hitting the reset button, doing A, followed by what you wrote down on the piece of paper. Okay? So when you think of associativity, it's quite tricky. But if you can check that this multiplication is associative. All useful stuff in physics so far has been associative. Now, it's easy to see a non-associative system. I want you to always, when you hear the teacher tell you, well, that's associative or commutative, try to think of something that isn't. Can anybody think of a non-associative operation? Well, what people call, slash division. Okay. You'll get a different answer if you do 3 divided by 4 divided by 5 in that order, as opposed to doing 4 divided by 5, remembering the number, then dividing 3 by the number you remembered. In other words, this does not equal this. And that's the paradigm for all non-associative systems. They're called norm division algebras. But they don't appear to be useful in physics. This is. And all symmetries are associative, but they're not generally commutative. Now notice there are subgroups in here. If I just ignored the reflections, I just have rotations, and they form this little 3 by 3 bit up here in the upper left corner. And they also form a magic square, and I can do A times B and get C. And so that forms the set of rotations in the plane. The set of rotations in the plane form a symmetry group. But it's sitting inside of a larger symmetry group once you allow the reflections, which sort of require you to come up out of the plane and go back in again. And actually, this is an example of a commutative group. These rotations in the plane do satisfy A times B equals B times A. So symmetries often have subgroups. And notice there's also something here we call parity. This thing knows about the difference between what lives in the plane and what doesn't in a basic way. Suppose that we identified all the rotations by the number 1. Then 1 times 1 would give back 1. But we could identify the reflections by the number minus 1. Then minus 1 times minus 1 gives back plus 1, a rotation. Furthermore, 1 times minus 1 gives minus 1, which is a reflection. So we say that the reflections have odd parity. They're different. The triangle knows, although it has this symmetry, that some of the operations are different. Those are the ones that you have to lift out of the plane and come back from. And all of that is encoded in this remarkable structure. Now let's talk for a moment about a continuous symmetry. So here I have basically this is the equation of a circle. So I would have a circle of radius 1 here. And I take a given vector whose x-axis, whose x-coordinate is x, y-coordinate is y. And if that vector lies on the circle, then x squared plus y squared equals 1. I can do a symmetry transformation that rotates the circle into itself and rotates that vector through an angle theta to a new vector. The new vector will have x prime and y prime for its coordinates, and that new vector must satisfy 1 equals x prime squared plus y prime squared, because it's on the circle. What's the transformation? Well, this, of course, is the heart of trigonometry. the new coordinates, y prime and x prime, are related to x and y through these equations. Y prime cosine theta plus x prime sine theta gives the new y, gives the old y. X prime cosine theta minus y prime sine theta gives the old x, and you can check that. But here we have an example of the symmetry of an equation. So in physics, we might have an equation like F equals ma or something like this. And we notice if we take the variables in the equation and we replace them by new variables through this relationship, we get back the same equation. And it's easy to check that by taking x and substituting x prime cos minus y prime sine, taking y and substituting y prime cos plus x prime sine, forming the squares, doing a little algebra, using the fact that cosine squared plus sine squared is 1, and you'll see that x squared plus y squared equals x squared plus y squared. So what we have found here is a little more abstract. Yes, there's an underlying geometrical picture of what's going on, but the equation written in these variables is the same as the equation written in those variables. And this is a coordinate system independent equation. It really says that it doesn't matter which variables you use. You could use these variables or that variables to talk about a vector because they're related by the equivalence transformation, by the rotation of the circle. We'll come back to an application of that in a moment. So what the mathematicians were able to do was to classify all continuous symmetries. And they did this in the 20th century, late 19th, early 20th century. What they found is that the continuous symmetries form 4 classes. And basically, these are kind of the basic things you can build. You can build up more symmetries from this. But the simplest is starting with the circle, which is called SO2. You can go to the sphere, which is SO3. You can go to the 4-dimensional sphere, SO4, and so forth. So spheres in any number of dimensions form symmetry groups, collections of operations that leave the object invariant. If you want to talk about the sphere in 4 dimensions, for example, you had x squared plus y squared plus z squared plus, we'll call it w squared for the 4th coordinate. And all of those points live on the surface of the sphere. So that defines a 4-dimensional sphere. SO4 says there's a bunch of transformations with a bunch of angles that allow you to map to a new point such that the new coordinates also lie on the surface. So that x, y, z, and w equals some big matrix multiplying x prime, y prime, z prime, w prime. There's a linear matrix transformation of 4 coordinates to 4 coordinates that leave you on the sphere. That's SO4. Now, as I said, these things are called the compact groups because they define, in this case, a sphere with a finite surface area. I could also change a sign here, which we do, put a minus sign there, and I'd be talking about SO3, 1, which is just SO4 with one of the plus signs replaced by a minus sign. And now, there's also a transformation that gets me from here to here, but I'm on the surface of a hyperboloid. And the hyperboloid doesn't have finite surface area. So I can get to other symmetries from these, but I have to give up the compactness. Then you can say, what about complex spheres? Well, that's where the coordinates are complex numbers. In a complex sphere, the x-axis is now complex number x, complex number y, z, w. And we take the absolute squares of the complex numbers. And that defines SU4. That defines the transformations of a sphere in 4 complex dimensions. And you might ask, why is that useful? It turns out quantum mechanics is defined by complex spaces. Quarks come in 3 colors. What that really means mathematically is there's a 3-dimensional space called color space with 3 complex directions. We call one red, call one blue, we call the other green. And the symmetry of the sphere is SU3. And that corresponds to a red quark being rotated into a blue quark, or a red quark being rotated into a green quark. And that is an exact symmetry of the force laws between quarks. A red quark interacting with a blue quark, turning into a blue quark, emits a gluon with the same strength as a green quark rotating into a red quark. That's a symmetry that defines, in fact, the force laws between quarks. So, and then there are these other groups. All right. What good is this? Here's a problem. Might be on your SAT test. Here are three objects. Let's call them masses. At the center, everything's static here. The three masses are arranged on the vertices of an equilateral triangle. At the center, I put a mass. What is the force exerted on the mass at the center by the three masses on the outside? Who said 0? Why?
Because they all cancel out.
And that's what you find by doing the calculation, or how do you know that?
Just, I don't know a lot for physics.
Okay. You could do the calculation. And I've taught physics many times, places like Caltech and so forth. And what happens is the students start adding this vector up, that vector, and that vector. And they usually will make a minus sign because it's kind of a tedious calculation error, minus sign error. And they'll get a result like that. And so their homework gets turned in, and I say, it's not right. Fortunately, you would have gotten it right. Why is this answer wrong? Well, the answer is wrong because this system has the symmetry of our equilateral triangle. In particular, I can do a reflection about axis 1. Remember good old axis 1? I just draw axis 1 and I reflect it. I'll get the same physical system back. But my answer has reflected from this into this. Remember, every point gets reflected into an equivalent point on the right side. And so that answer is different than that answer for the same system. You can't have two answers for one system. So that answer is wrong. So telling the student this, they'll go back and redo, oh, I found my minus sign error, and I get this answer. But now, that's consistent with reflection about 1. But the symmetry is bigger than that. It also involves the rotation through 120. And so if I rotate through 120 degrees, that goes into that. Has to be, can't be both. So this component of the vector is ruled out. And once we've ruled out that component and that component, we've proven the answer is 0. We didn't have to calculate anything. So symmetry is that powerful. Now suppose, I was easy on you. I asked for the gravity case. Suppose these are 3 nucleons inside of a nucleus, lithium or something, lithium-3. And that's a pion sitting at the center of the system. What's the force on it now? By the way, there are no spins or any other degrees of freedom. Everything's just as you see it. What's the force on a pi meson sitting at the center of 3 nucleons, 3 neutrons? That's 3 protons, whatever. What's the force? You gave me the answer before. Still 0. What if these are 3 black holes and that's a spaceship caught in a horrible region of space? 3 monstrous black holes. It's not Newtonian gravity, it's general relativity. You're almost at the horizons of these 3 black holes. What's the force at the center? 0. Symmetry wins. It's more powerful because it underlies all the laws of nature. So you can already solve problems in general relativity. Quantum mechanics, you can solve these problems because of symmetry. Now you got to be careful. If this thing had a spin like that, and that one had a spin in a different direction and so forth, then the symmetry would be broken. You might not, or maybe this is a snapshot at one time instant of 3 things that happen to actually be moving that just happened to be at that position, that configuration at that time. But that's not a symmetrical situation because they actually have velocity vectors. Then it wouldn't work. But in the cases, the special cases where you have symmetries, it works. Now here's an astonishing fact. I don't know if I actually do it here, but I'll just tell you the answer if we go to the next one. All right, so the force is 0 by symmetry. We said these are 3 masses, and we put a mass at the center and we did gravity. Okay? What happens if I push this mass a little bit away from the center? what happens? If I push it that way, to the top, upward direction, what happens? Well, now these two things are closer, so the force of attraction between them is greater, and the force of attraction here is weaker, and we know at the center, by symmetry, the answer is must be perfect balance, 0. So therefore, this system will start to run away. If you think about it, if you push it this way, it'll also run away. And that means it'll run away in almost any direction. If somebody sneezes, you have this situation of 3 masses with one at the center, and somebody sneezes, tiny perturbation, the system is unstable. All static gravitational systems are unstable. You can find equilibrium configurations like this, but they're not stable. Now, let's use Ben Franklin, who invented the concept of electric charge. Suppose these are all positive charges. Now let's put a positive charge at the center. This is what happens in a molecule with the electrons orbiting at large distances, and the 3 nuclei are all positively charged. The nuclei feel each other, so plus, 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 and plus at the center. This would be like a CH3 molecule. Is that methane? It's not quite methane. CH3 radical. Now what happens? Same argument. Why doesn't the system collapse? Why is CH3 stable? Because now, if I push the carbon close to that hydrogen, the force of repulsion pushes it back. Force of repulsion pushes it back. So now what happens is the thing is actually stable. And it'll sort of oscillate around the center, but it'll always get pushed back. If you don't have repulsive, this is sort of weird, but if you don't have repulsive forces, you can't have a stable world. If all forces were attractive, the world would always collapse. It's the repulsive interactions that maintain stability and allow chemistry to exist, this equilibrium between